All right. Good afternoon, everybody. Today, or good evening, good morning, whenever you're watching this. The today's review session is going to be over the magnetic fields and moving charges questions from the multiple choice set I assigned earlier this week. So let's go ahead and get started. Number one, a charged particle of mass m and charge q is injected into a region of uniform magnetic field that is directed into the page as shown above. So sometimes they will tell us what kind of direction the field is pointing in. In this case, we can see the axis. Oh man, I need to remap my pen settings. This is all messed up. Oh, the heck? Because it looks like it's scaling the area in which I'm. No, it's correct. Oh, it's because I have it upside down. Because that's right, I'm left-handed. Whoops, rip. I am a fool. Sorry about that. I'll probably have to edit that out of the video. Anyways, okay, now it works. Okay, so they're going to inject it into this magnetic field that has a velocity in this direction. The magnetic field is into the page, so the force is going to be in a plane perpendicular to this. So then the force is going to be either in this direction or that direction. Looking at the picture, it is to the right. And so the question is, though, if we happen to choose a second particle with a mass of 2m, how would that describe the relationship between the two radii for these trajectories? So recognizing that the magnetic force, which is Q, V, B, and that's going to be the centripetal force in this scenario. We have no gravitational effects, any of that. So when we do Newton's second law and net force, that's the only force, equals m times a, the acceleration here is that special centripetal acceleration. And so at the end of this, we just have to determine, well, what's changing? The only thing that's changing is the mass. So if we get rid of all this, we can go ahead and say that the mass is going to be proportional to the radius of the circular path. I just kind of went ahead, and if you want algebraically, we can see that if we solve for the mass is going to be QVB, and then sine and theta, they're perpendicular, so I'll just leave it as the magnitude here, divided by V squared times R. Nothing else is changing in this problem, so all of this quantity here essentially is irrelevant in the comparison, so we see that the mass and radius are directly proportional. Twice the mass gives us twice the radius. Let's go to the next one. Here we have another scenario. Again, we're injecting particles with a certain velocity into a region with a magnetic field. In this case, the magnetic field seems to be pointing towards us or out of the page, as convention says. And so they move initially with a constant velocity, and they're talking about this region here. The scientists wish to temporarily confine the particles in a uniform magnetic field of magnitude B. The region of the magnetic field has a horizontal range x, as shown here in this portion of the diagram or the figure. To confine the particles, the scientists switch on the magnetic field at the moment when the particles reach the center of the horizontal page. So it was traveling along at a constant velocity, and then they turn on the field at this point, smack dab in the middle. And they want us to determine which of the following is a correct prediction of the results in the experiment. Looking at how the question or the answer choices are provided, they're all making arguments about B. So let's go ahead and take that equation from before, QVB being the centripetal force. Let's go ahead and rearrange it. Again, we are fortunate. The velocity and the magnetic field vectors are perpendicular. This is B, this is V. If we were to look at it in some kind of isometric view, rotated towards us. And so the force is going to be perpendicular to the plane created by these. So we're going to have either a force in this direction or down in this direction. They've gone ahead and drawn the circular path. So that tells us that the force here is going to be locally upwards, but it is going to change in direction, varying the entire time in its direction. So what's the takeaway here? Well, we're going to need to go ahead and solve for that magnetic field. What's the radius? Well, the radius of this circular path is x over 2. So we get QVB, sine of theta being perfectly 90. equals mv squared over r. We solve for b. B is going to be mv squared over qvr. Again, those guys are going to cancel. And we just make that substitution. So to get this to move around in a circular path such that the magnetic force is the centripetal force with this radius as a result of resulting in our circular path, the expression should be something like this. Looking at the answer choices, we recognize that none of them have an x divided by 2. Be careful, these are not it, because the bottom of the bottom will go to the top when we rationalize our fraction. And so it looks to me like if the force happens to be this magnitude, it will perfectly remain in the region. Anything greater than that will ensure that the circular path is going to be definitely within that region. We might, let me use a different color here. If the force is, or if the magnetic field happens to be greater than this magnitude that we've calculated, then it's still going to be confined to the region, just in a smaller trajectory. So let's see here. So not that one. If B happens to be greater than this quantity, which we derived right here. Okay, then it will be confined. So answer choice A. Very good. Next one, again, more trajectories. Students want to find the direction of a uniform magnetic field in their experimental setup. They direct electrons from the left side of the page into the setup and observe the path that they take toward the top of the page as shown. Which of the following is the correct prediction for the direction of the magnetic field in this region? So ultimately, we are not being given. Oh, yes, we are. I was going to say, I was like, I don't remember reading anything about charges, but it's right here. It's electrons. So be careful. We'll have to keep that in mind for our right-hand rule. So what is this result here? Well, we have B this way. F is in this direction. So B must be perpendicular. It's either going to be pointing out of the board or into the board. Sorry, I like, as I was saying them, I wrote them in like opposite directions or in opposite order. But yeah, out of the board, into the board. So let's go ahead and see here. Well, we do our right-hand rule. I cannot capture that for us here, but you stick out your right hand, point your finger along V, if you will. And then so that our thumb happens to point up in the page for an electron, I think that the magnetic field is, give me 1 second, it's going to have to point out of the page. Initially, when I stick my hand out and I point my finger along V and I direct my, and I rotate my hand so that my thumb is directed upward, my middle finger, which in our class represents the magnetic field, is going to be pointing into the paper or into the page. But remember, these are electrons, we reverse the direction. All righty. An electron enters a region that contains a uniform magnetic field. The electron is again deflected in the direction that is shown in the figure. Which of the following represents the direction of the magnetic field and provides supporting evidence? So I think we saw earlier that the conclusion was that it was out of the page. So again, it's out of the page. I think I'll spare us that time. More about the reasoning here, because the electron is deflected toward the top of the page. That is the evidence that we are seeing here. If the force happens to be this way, F, and then the velocity was in this direction, then B for an electron should be out this way. Oh, whoops. That's wrong. It says toward the top of the page. I didn't even read the first part because I just assumed, because I did not see the end of the page. There we go. Okay. Because setting mv squared over r equals qvb indicates that the centripetal force is in the same direction as the magnetic field. No. This part is true as a physics principle for this scenario. That is an equation that applies, but this is not the supporting evidence that works. It being the centripetal force is kind of weak. So, I mean, I think we do recognize that the centripetal force is that magnetic force and it's upward, but I think we should probably be talking something more about the right-hand rule and the directionality relations between all of these vectors here. They should all be perpendicular to each other. Because, Using the right-hand rule, the magnetic force would deflect the electron toward the top of the page. I think that's a better answer than D. Alrighty, 5, maybe something a little bit more interesting this time. An ion separator consists of a uniform magnetic field that is directed into the page, into the plane of the page, and two conducting plates that can be charged with equal magnitudes but of opposite sign. A student wants to launch negatively charged ions into the ion separator with a velocity v such that the ions pass through the separator undeflected. So we have to be careful because in this instance, this electron, if this happens to be positive and this happens to be negative, without the presence of this magnetic field, it's going to accelerate in that direction. So that's where the ion separator comes in hand with its magnetic field. However, the student wants to launch positively charged ions at a velocity v such that the ions cannot pass through the separator. Okay, that's pretty interesting. So they want to only send through negative electrons or negative charges. We'll see what happens. The magnitudes of the charge for positive ion and for a negative ion are the same in this experiment. Okay, nice. So the magnitude of the charge is going to be plus or minus an electron's worth of charge, if you will. Or plus or minus Q, I think is better. We're not told that they're specifically electrons or protons or whatever, but plus or minus Q. Shoot, it could even be plus or minus 2Q. Some, it doesn't matter. We get the idea. The magnitudes, let's see here. Based on the figure, which of the two plates, if any, should be positively charged and why? Okay, so we're gonna have to be careful because we're gonna have to make sure that whatever we choose here is consistent for both a positive and a negative charge. So let's go ahead and see here. So B happens to be into the page. V happens to be to the right. So the force is going to be perpendicular to the plane created by those two vectors. We do our right-hand rule. For a negative charge, normally the magnetic field here is going to create a force on a positive charge that is up. But because the electron is involved here, the magnetic force on the negative charge, sorry, not electron, is going to be down. Now let's go ahead and think about it. Okay, for a positive charge, well, we can do the right-hand rule, V to the right, middle finger into the page, and thumb extends naturally up as expected. Okay, so these should point in opposite directions for the magnetic field force. Now let's go ahead and see how we would get the negative charge through this combination of plates and magnetic field. Well, for a negative charge to pass through undeflected, the downward magnetic force on the negative charge is going to have to be balanced by the electric force pointing up. Oh, sorry. The force on the charge pointing up. Well, ooh, I don't know what I did there. Let's bring it back. And so this is going to be the electric force. And so it looks to me, in this case, we should put positive charges over here. And so that would make this positive, negatively charged on the bottom. Okay, I think we're getting the gist here. Okay, well, what happens when we do this with a positive charge? Well, for a positive charge, the magnetic force is going to be up. And for the electric force, therefore, we are going to need a downward direction. So in this case, they should both balance out. QVB equals QE. That's the electric force equals the magnetic force. And in this case, if we want an electric force down, we'll check it out. Negative charges are going to work here as well. And so the negative charge that would attract that positive charge here and repel this negative charge are going to be consistent in both scenarios. So this brings up an issue. At the end of the day, we will end up balancing these electric forces on a on the negative charge, but the same thing's going to happen on the positive charge, because again, the magnitude of these forces are determined by this relationship or these relationships. And at the end of the day, actually, the charge doesn't even matter. So if we're able to allow these charges to travel forward undeflected, whether they're positive or negative, it's going to happen. So I think our best answer choices are either D or E, because the situation cannot created with the plate shown. An electric field must be oriented parallel to the plane of the page. I don't agree with that statement. Let's see the next one. Neither plate, because this situation cannot be created. If the electric force and magnetic field for the negatively charged ions cancel out, such that the ion travels through in the region undeflected, the same would also be true for the positively charged ions, as we were saying. So a lot of work, a lot of consistency. This is usually kind of considered a conceptual question, but it tests a lot of really good concepts together. So it's good to, I mean, know this principle, the answer, but you can always arrive at it. Okay, 6. A positively charged particle travels horizontally northward and enters a region where a field may exist. This region may contain only a magnetic field, only an electric field, or both a magnetic and an electric field. When the particle enters the region, the particle does not speed up or slow down, but it does deflect in the downward direction. Which of the following statements is correct about the field or fields within the region and provides correct reasoning? So because the particle does not speed up or slow down, automatically the force, if there is one, because it does change motion, the force must be perpendicular to the velocity. So regardless of how the electric field is oriented, it would automatically accelerate. So it cannot be strictly an electric field, because if it does enter an electric field, let's say this is my velocity, let's say this is a positive charge for whatever reason. If it were to deflect down and we said that the electric field was down, well, then it would accelerate like a projectile. So it cannot be an electric field alone. If an electric field were to exist, it should probably be balanced by a magnetic field, much like we've seen in this previous example. Now, for the magnetic field, I think a magnetic field can exist on its own, because we've learned that when a magnetic field acts on a moving particle, its force is perpendicular to the velocity. Now, here's the part I am a little concerned with is this deflection in the downward direction perpetual? Like, is it always going to be downward? Or is it just initially? So let's go ahead and maybe look at what if the magnetic force and the electric force balance out perfectly? Well, in that case, it's not going to speed up or slow down, but at the same time, it's not going to deflect downward. So to have deflection, it must have some amount of force to change the direction of motion. But this force is going to be perpendicular to the velocity. So let's see here. It's positively charged. So velocity is this way. The force is down this way. The velocity happened to be northward, I believe, because it was traveling northward. And then so west is going to be into the page. East is going to be out of the page. In case, like north, south, east, west. Okay. So to get this, we can do our right-hand rule. We're going to have a downward force. Our thumb points down. Our velocity happens to be to the right. With a right-hand rule on a positive charge, the field should be pointing out of the page. And so I believe that should be a eastern. Let's see here. Now looking at this, they're talking about southward. Only a southward electric field is present because an electric force will bend the particle parabolically. My only concern is that, again, it's going to accelerate. And so can I talk that is like why it's wrong. Only a southward electric field is present because an electric force will cause the particle to undergo circular motion. Ooh. Only a southward magnetic field is present because the magnetic force will cause the particle to undergo circular motion. I just don't think it's perpendicular to the velocity. So that's my main concern. It's not going to feel the force when it's not perpendicular to, or the field's not perpendicular to the velocity rate component. Only a southward magnetic field is present because the magnetic force will bend the particle parabolically. Southward electric field, so there we go. And an eastward magnetic field are present because then the forces will cause the particle to deflect without accelerating. So that's the combination here. It's gonna also, hold on, let me see here. As it goes downward, my concern is the southward electric field, because it's gonna keep it from slowing down sideways. And so, okay, so they do want it to deflect downward, kind of like in a parabolic trajectory, or not really, but my concern is when it's right here, it's going to slow down, in my opinion. That's the only problem I have, is that the electric field is going to be southward and it's going to be slowing down because it's going to be attracted. Oh, no. Yeah, because if the electric field points southward, then that tells us that the electric force on a particle is going to be south. So I'm a little questioning of this one, but I think E is our best answer choice. Go ahead and move on to number 7. So more particles in some kind of magnetic field region, and they deflect upwards, with Q2 having a larger radius of curvature. And so it's all the same prefacing as before. So particle with charge Q1 follows the solid path, and the particle with charge Q follows the Q2 follows the dashed path as shown in this figure and label. Which of the following could represent the relationships between the masses and the and charges of the two particles and provide the supporting evidence? Well, again, QVB equals mv squared over r. And so if we look at this, R is going to be, and they want us to have a relationship between the masses and the charges. So at the end, the velocities kind of cancel out, the magnetic field cancels out, and I think the proportionalities here is better written as Q is going to be proportional to m over r. The other parts don't really matter, but we're going to be looking at these radius. So or radii, we know that the radius of curvature for charge 1's path is going to be less than the radius of curvature for charge 2. So that's going to be m1 over q1 is going to be less than m2 over q2. In case you were wondering, I kind of said R is then going to be proportional to m over q. Okay, so let's see here. M1 equals twice M2 and Q1 equals twice Q2. If that happens, those proportionalities of 2 over 2 cancel, and that's going to give us the same radius of curvature. So that's not going to happen. The radius of curvature will not decrease if that is the scenario. If we look at this, if we had solved this equation for R, R equals mv over q. So if this goes up by 2 and that goes up by 2, the fraction doesn't change. Mass 1 equals twice m2, q1 equals twice q2. And they say again, the radius of the will decrease. Again, that cannot happen. The radius is increasing for q2. M1 equals M2. Okay, let's see what happens there. And charge 1 happens to be twice that of charge 2. So what they're saying here is that, okay, well, don't even worry about the mass proportionality. If we double the charge, well, we double the radius. Or sorry, it's inversely proportional to charge. So if we double the charge, the charge goes up by 2 times, then the radius is going to go down by 2 times because they're inversely proportional in that scenario. So as the charge increases, the magnetic force increases. That's true. The radius of the path will decrease. I think that's our best answer choice. Here they're telling us that, again, it's twice as much, and no. They just changed where the twos were in this case. All right, so D is our best answer choice. 8. So again, more particles, more trajectories as they move through a magnetic field, and they want us to talk about which of the following claims can be supported by the figure. And we know that the magnetic field is going to be directed out of the page as shown by these dots. Okay. Okay, so they tell us that particle 1 has a positive charge, particle 2 has a negative charge. Absolutely not. Their deflection or their forces point in the same direction. So, and they have the same velocity and the same magnetic field. So that cannot be. They must have the same charge. Particles 1 and 2 have charges of the same sign, but it cannot be determined if they are positive or negative. I think we can definitely determine. We know that the force is this way, the velocity is this way. So then we do our right-hand rule. And so this is when we do our right-hand rule, be along the middle finger pointing out, our velocity to the right, and our thumb pointing down. We don't have to change anything, so that's going to be a positive charge. We can determine. Particle 1 has a greater mass than particle 2. No, if anything, we have seen that R is going to be equal to mv over qb. The more mass we have, the more radius of curvature we have. And particle 1 has a smaller radius of curvature, so not true. These are best answer choice. Another charge in a magnetic field, in this case, a positive charge moving into a region with a magnetic field pointing into the page. Which of the following modifications to the experiment will allow the proton to travel through the region with a constant velocity and provides the reasoning? So if we look at this with the right-hand rule, again, initially, the magnetic force is going to be upwards when it enters. So the electric field should be downward. Oops. The same question asked again and again in this review, just in different ways or applying different skills. In this case, so here we have to change the experiment instead of running an experiment. Change the velocity of the proton so that it travels into the page because then the magnetic force on the proton will be 0. Ooh, I think that works. Let's see if there's better answer choices. Because again, in this case, sine of 0 degrees is 0. So QVB sine theta, when we write it out in the magnitude or polar form for the cross product, that's 0, the force is 0, makes sense. Change the direction of the magnetic field so that it is directed toward the top of the page. All that's going to do is create a force that points in another direction. It's still going to accelerate, so no. And that's the key part. They want constant velocity. That means no acceleration whatsoever, not just constant speed. Create an electric field that is oriented in the same direction as the magnetic field, because then the electric force will cancel out the magnetic force. No, it must be in the same or in the opposite direction, sorry, as the magnetic force. Create a second magnetic field that is directed toward the bottom of the page. No. Increase both the speed. Remember, they're taking advantage of you're looking for some kind of force that points down. So here they're kind of expecting you're going to read it a little quickly, maybe get a little mixed up, not think about the fact that a magnetic field that would be directed down the page would create a force that's pointing either into the page or out of the page at that point. Increase both the speed of the proton and the strength of the magnetic field because the magnetic force can overcome the inertia of the proton. Very unlikely. And even then, there will still be some acceleration, even if it's, minute. It would have to be like some Planck acceleration for us to get away with that. Okay. In an experiment to test the magnetic force on moving charged particles, 3 charged particles enter the field with the same velocity and move in a straight line toward the right side of a lab table. The charges on particles 1, 2, and 3 have values of Q1, which is 3 times the positive Q value, Q2, which happens to be 3 times a negative Q value, and Q3, which happens to be a plus 6 Q charge, respectively. The forces on the particles are F1 equals F2, which are both greater than F3. Which of the following correctly ranks the magnitude of the magnetic force on the 3 particles? What? I think they're moving with the same velocity and move in a straight line towards the right side of the lab table. I don't think I understand this question because literally I would just like to choose. Oh, wait. No, yeah, they give us a comparison. The forces on particles 1, 2, and 3 are F1 equals F2, which is greater than 3. I don't think I mean, is that supposed to be our answer? I don't know. We'll skip this question. This one is kind of, I don't, I just, okay. Let's go to 11. I'll look at the scoring guide. As a matter of fact, let's go look at the scoring guide, see what they, oh, shoot, I did not attach it here. Let me put it at the bottom of the page. Scoring guide. Oh, I think I downloaded the different scoring guide. Yeah, this is for forces on wires. Whoops. Okay, my mistake. Well, I don't have that one ready to go, so we'll go ahead and call it. Like look on that one, look up that one later. Okay, we're almost done here. So looks to me kind of like another voltage selector. We have particles moving to the right, an electric field that is directed upwards, a magnetic field, sorry, that happens to point out of the page. An experiment is set up to determine the speed of charged particles as they move through a region that is traversed by a constant electric and constant magnetic field. The particles are moving toward the right of the page when they encounter the region. The electric field points toward the top of the page and the magnetic field points out of the page. Predict how the positively and negatively charged particles of various speeds will behave in this experiment. Okay. So here they're talking about B equals EB. So again, they've taken the electric force magnitude equation and the magnetic force magnitude equation. And we're going to balance them out if they move in a straight line. And what velocity would that be? So the velocity, as we have seen, is going to be E over V. Okay. Particles with a speed equal to V, with speed V equal to E over V, will pass through the region with no deflection. Speeds are particles with a speed greater than that. So let's say that goes up. Okay. Will be deflected toward the bottom of the page, regardless of whether the particles are positive or negative. Okay, so let's go ahead and do a right-hand rule for the positive particle real quick. So if the velocity is bigger, so if V increases, the magnetic force is going to increase, and therefore there will be deflection in the direction of that. So let's go ahead and determine the magnetic force on these if it's a positive particle. Point your finger along to the right for V. The magnetic force happens to point out of the board, which is going to be our middle finger, and then our thumb points down. So it would be deflected downward. And sorry, here, these arrows mean increases. This is, let me say, the direction. So, oops. So the magnetic force on a positive charge is going to be downward. On a negative charge, it's going to be in the opposite direction. It's going to be up. Okay. So, not true. Okay, so if it's equal to, it will pass on with no deflection. Positive particles with a speed equal to that will be directed. will be deflected toward the bottom of the page. Negative particles with a velocity equal to that will be deflected. No, at this special velocity, it goes undeflected. As a matter of fact, look at this. This question is just inconsistent. They say it will pass through with no reflection, but then they're telling us that if it is equal to, like in their previous statement, now it will be. So maybe I'm just tired and I'm reading this incorrectly, but this just seems like inconsistent. All right, so they would pass through the region with no deflection. Positive particles with a speed equal to that will be deflected toward the top of the page. So again, not going to be it. They just took these and reversed the toward the bottom and the top. So I don't think that one's good either. Here, this one, positive particles with velocity greater than that would be deflected toward the top of the page. I don't think that part is correct because in that case, the magnetic force is the bigger part here. And so at the end of the day, I don't think that is correct. They were going to be deflected toward the bottom of the page and negative particles will be deflected towards the top. There's our best answer choice. Okay, 12. Last one. Oh, shoot. I'm sorry. I just saw the chat. Oh, okay. I already just, yeah, in reference to that previous question. Yeah. Maybe they were just running out of options. A proton travels through a region with a uniform magnetic field and a uniform electric field passing through a parallel plate capacitor as shown in the figure. The proton enters the region traveling east, moves through the fields undeflected, and continues to travel east after exiting the region. What is the direction of the magnetic field? Sounds to me like, well, there has to be a magnetic field here that causes it to move undeflected. Because originally, if this is a proton, the electric force is going to be up. That's a really funky. And therefore, to travel undeflected, the magnetic force should be pointing down with equal magnitude. So if we do the right-hand rule, velocities to the right, we need a downward force. So our thumb has to point downward when we do our right-hand rule. So we rotate, and then it looks to me like for a positive charge, this is going to be pointing out of the page. Okay. So I think that is it for that one. My main concern is this part. It continues to travel east after exiting the region. So what the heck is going on here? Because I'm going to assume here that when they say passing through a region with a uniform magnetic field and electric field, they mean that the magnetic field is only uniform in this region here. And the magnetic field stops after that region. Okay. So I think that's it for this one. We'll go ahead and call the recording, the session here.